what we will talk about are view factor rules. So there's certain rules that apply to view factors that you can use to establish their values once you know other view factors in the system. So we'll talk about, I think, two of these, the two common ones. So the first one is called the enclosure rule. Okay, so the idea here is, let's say we have some enclosure. We have maybe a three-surface enclosure, so we'll call this surface 3. We'll call this one here surface 2. We'll call this one surface 1. So if we think about, let's say surface 1 is emitting some radiation. It's emitting radiation inside this enclosure. And we'll treat the outer surfaces as not emitting. Right? We aren't concerned what's happening on the outer surfaces. So just the inner surfaces inside this enclosure. So if surface 1 emits radiation, there's kind of three possibilities of what can happen. Right? It can hit surface 1, it can hit surface 2, it can hit surface 3. So all those things, the sum of all the possibilities have to add up to 100%, right? So that's basically the premise of the surface or the enclosure rule. And when we write it out, it just is as follows. We say the view factor from surface 1 to surface 1 plus the view factor from surface 1 to surface 2 plus the view factor from 1 to 3, those all have to add up to 1. Right? And again, all that's saying is you emit a photon inside this enclosure, it has to do one of three things. The probabilities of each of those have to add to 100%. So that's the enclosure rule. Things to point out here are, be careful about how you're writing indices here. So I'm saying we're going from 1. Anything that's emitted from 1 has to go to one of three surfaces. So we're always writing it from 1 to another surface, right? From 1 to another surface. You can do this for surface 1. You can do it for surface 2 equivalently, right? So this would just be F21 plus F22 plus F23. That equals 1. All right, so you can do that for each of the surfaces. It's not true, though, if I write F12 plus F22 plus F32, that is not necessarily equal to 1. Because we're talking about what's coming into that surface, and that doesn't necessarily have to equal. It's always from the surface to all other surfaces that it has. Questions on that? Okay. So that's the enclosure rule. The second rule here would be reciprocity. So reciprocity is actually probably one of the most powerful rules or powerful tools that you have to evaluate view factors. The idea for reciprocity is, let's see, let's go through this. So let me just draw two surfaces over here. So we have two surfaces. They're at some angles in space. And I have from surface, we'll call this surface I, and we'll call this surface J. So I have a radiation coming from surface I that's going to go to surface J, and that radiation is going to be Fij times AI, right? And that's that radiation. The amount of that radiation is going to be then times sigma t to the fourth, right? So that's the power going from I to J. The view factor times the area of the emitting surface times the emissive power of that surface. Right? So coming back from surface J, we have radiation as well, right? There's exchange happening here. So that's going to be, similarly, it's going to be Fji times Aj times sigma t, tj to the fourth. So this is ti to the fourth down here and tj to the fourth. So we have this net exchange of radiation. So we can actually write an equation, an energy balance, say on surface I for this. So if we do that, let's see. So let's write an energy balance on surface I. So Q dot from I to J, going to be our net radiation exchange from I to J. That's going to be what? That's what's going, Fij, Ai, sigma Ti the fourth, minus what's coming back, which is Fji, Aj, sigma Tj fourth. Okay, so reciprocity is this idea that we need a relationship between the view factors and the areas in these two surfaces. If we look at this equation, we can think about a kind of a special case where Ti and Tj are the same temperature, right? And it's kind of like, why would we do that? But we'll see where we're going. So let's say that a special case where Ti is equal to Tj. So in that special case, we end up with Q dot I to J is equal to 0. All right, if Q dot I to J is equal to 0 in that special case, then we see that this equation becomes 0 is equal to Fij, Ai, sigma Ti the fourth, minus Fji, Aj, sigma T, I'm going to write Ti to the fourth because Ti is equal to Tj. So if they're both the same, sigma Ti to the fourth, that actually can cancel out. Right? And we're left with this statement that Fij, Ai is equal to Fji, Aj. So we've used this special case to come up with this statement that the view factor from I to J times the area of I is equal to the view factor from J to I times the area of J. So if that's true in this special case, it has to be true in the original equation, right? Even when Ti is not equal to Tj, this still has to be true in order for this result to happen. And if you don't believe me, we'll think about what's happening. If Ti is not equal to Tj, what happens to Q dot I to J? That responds to that temperature difference. So Q dot I to J is always going to balance that difference between Ti and Tj. Right? The other view factors and areas, those aren't changing. Right? Those are constant for the problem. So from this, we can make this observation that this is true. Right? If this is true, this is our reciprocity. If we, at some point, compute, say, Fij, and we know the areas of the surfaces involved, we can always get, say, basically for free, right? We can always get that other view factor. Right? So that's a really powerful tool that you have for evaluating these things. Okay, questions on that? Okay. So, all right, those are our rules. Enclosure rule. You get 2 of 3 surfaces, or 2 of n minus 1 of n surfaces. You can always compute the last one in an enclosure. Reciprocity. If you get 1 view factor in the areas, you can always get the other view factor. So those are 2 tools. One thing actually to point out here on this enclosure rule. So let's say we have a situation like this, where we have 2 surfaces like this, and they're just open to the surroundings. Can we use the enclosure rule in this situation? Seeing some nods, yes. So people have had heat transfer before, right? We can put in a fake surface here, right? Put a virtual surface in here. And that virtual surface, it has its own view factors associated with it, but it doesn't have to actually be an enclosure. It just has all the edges of this region just have to add up to enclose it. So you can still do the enclosure on not enclosures. All right, let's talk for a second here about this cross and uncrossed strings method. This is, again, kind of a not obvious thing, but it's kind of interesting when you see what's happening. So the idea for cross and uncrossed strings is, let's say we have 2 surfaces. They don't have to be flat surfaces. They can be kind of anything. So let's just draw some random surface here, and then let's draw another surface down here. So you have these 2 surfaces that can see each other. With the method of cross and uncrossed strings, what you want to do is first identify the edges of each surface, or the bounds of each surface, and we'll label those. So here, let's call this point A. Let's call this point B. Let's call this point C. And let's call this point D. All right, so next step is we're going to draw strings or connections between the different vertices. So we start from A to D, so we'll draw a connection here. We'll go from B to C, draw a connection here. And then we're going to draw cross connections as well. So here from A to C, and then here from B to D. So the method of uncrossed strings says I can estimate the view factor, I can calculate the view factor between these two surfaces using the lengths of these strings. And the formula is AI, Fij, so let's call this surface I down on the bottom and surface J up on top. So AI Fij is again by reciprocity equal to AJ Fji. And the formula is W. So W is going to be length in and out of the page. So W times this summation of L crossed minus the summation of L uncrossed divided by 2. Right? And so for this example, it's going to be, so the crossed are going to be W times, crossed are L, let's see, L times AC plus L times BB minus LAP minus LBC. Right? All that divided by 2. So this is actually going to estimate the view factor between these two surfaces. Again, surface I to surface J. So yeah, it's kind of an interesting tool. The other thing that you can do with this, I'm going to copy this over here. The other thing you can do with this is, let's say you have a situation where, again, we have these two surfaces, and they can see each other, but there's an obstruction between them. So let's say we have, I don't know, somebody has a plate, and they introduce this plate in here like that. You can still calculate, with the method, you can still calculate the view factor with this. So again, we'll take our nodes, we'll draw like this. So we have now uncrossed, crossed. But then on this one over here, you actually just have to wrap the string around the object. So my length is going to be something like this. So you actually wrap it around there and you compute the length of the strings using that method. So all you need to know is the position of those of the sort of interfering object, how it changes the length of that string, and you can still use the same